Since the tutorial sheet is sent very recently, I don't expect you to solve the problems before coming to the tutorial class. So let us discuss one by one. So I may add a few more questions to this sheet, and this will be the last sheet. I have to add a few questions on Lebesgue integration, convergence theorem, and the abstract integration, which is yet to discuss. Of course, we have talked about abstract sigma algebra, measure, etc. in the beginning. Later, we concentrated mainly on a special type of measure called Lebesgue measure on R. Now we shall visit the abstract setting, sigma algebra, measure, etc. in the next few lectures. See, there are two ways of doing things. One is start from concrete and then go to abstract. On the other way, one can start with the abstract setting, discuss all the theorems in the abstract setting itself, and then go to concrete examples. But I prefer the first one, from concrete to abstract, because that will give you a more feel why this abstract theory is needed, etc. Okay. So I always prefer to have few concrete example. You familiarize things with concrete examples and then go to the abstract setting and ask how we can generalize these concepts. Okay. So that was just about the abstract integration. So don't think that we have only one or two class, then how we will. It's like we have done almost everything in the Lebesgue setting. So once you are okay with it, the abstract setting will not take much time. It is just extending to a more general measure space. That's it. Anyway, having said that, let us do a few more problems from this tutorial sheet 3. First question is, show that set of points on which a sequence of extended real valued measurable functions fn converges is measurable. A few things that you should bear in mind is that, first of all, when you talk about measurable functions, and more precisely a sequence of measurable function, there is no a priori assumption that it converges. You are just taking a sequence of measurable functions. The question demands to consider set of points on which the sequence of measurable function converges pointwise. That set may be empty. There may not be any point at which the set of measurable function converges. Whatever it is, you are asked to prove that that set is finally measurable. It may be null set, it may be full set R, or it may be something subset of R. Okay, so you have to prove that it is measurable. Any idea? I would also ask you to remind yourself the results about sequence of measurable functions. Once you have two measurable functions, its maximum is measurable, minimum function is measurable. Then we extended it to finite number. If you have finite number of measurable functions, their maximum and minimum is measurable. Then we went for sequence of measurable function and then talked about the limit supremum, limit infimum, supremum, infimum, etc., etc. Okay, so all those things were measurable. Okay. So this class of measurable functions is well behaved, both with respect to algebra and also with respect to topology. That means taking convergence, etc. If you have a sequence of measurable function, then if it converges, the limit function is convergent. Sorry, measurable. If it is not convergent, then you can talk about lim sup and lim inf. they are also measurable and so on. Okay, so keep that in mind. Now with that, can you tackle the first question? What is the set under consideration? Set of all points for which sequence Fn converges. Already I told that lim_sup and lim_inf of a sequence of measurables function is measurable. And what is the connection between convergence, lim_sup and lim_inf? Can somebody pronounce?
If is equals to lim_if, then the function is convergent.
If the lim_sup equal to lim_inf, then the sequence is convergent, right? So what is the set under consideration? So let me take Fn from, they have given extended real valued functions. Okay, so E subset of R. First, let us talk only about real valued. Okay, let us not go for extended real valued. For every n in n. And the set of interest is collection of all x in the domain for which limit Fnx exists, n tending to infinity exist. And you know that the limit exists if it is lim_sup equal to lim_inf. So what you are interested is collection of all points for which lim_sup Fn is equal to lim_inf Fn. Fn of x, to be more precise. This is the set of interest. And we are done. If Fn's are measurable, you know that lim_Fn function is measurable. Call it G. So G is a measurable function. Similarly, lim_inf Fn, call it H, is also measurable. So you have G of x is measurable, H of x is measurable, and the set under consideration is collection of all x such that G of x is equal to H of x, or G minus H of x equal to 0. Collection of all x such that lim_sup n tending to infinity Fn of x minus lim_inf n tending to infinity Fn of x is equal to 0. This is the set. Now G is measurable, H is measurable, therefore G minus H is measurable. Collection of all measurable function is well behaved with respect to algebra, plus, minus, constant, multiple, etc., etc. So G minus H is measurable. Now, let us recall the definition of measurability. A function h is measurable if for each real number alpha, collection of all x such that h of x greater than alpha is measurable, or h of x less than alpha is measurable, and so on. And also you have seen that if h is measurable, then collection of all x such that h of x equal to alpha is measurable. Yes or no?
Yes, sir.
But that is not if and only if. That's what I wanted to emphasize. See, h from E subset of R to R is measurable. It can be extended real valued also. If and only if collection of all x such that h of x greater than alpha is a measurable set for each alpha. That is if and only if. That is definition actually. Whereas we also know that h from E subset of R to R measurable. One-way implication implies collection of all x such that h of x equal to alpha is a measurable set. So measurability of a function is defined via measurability of the set. Actually, inverse image. I want you to keep this in mind. It is only if implies, and whereas this is if and only if. Okay. So nevertheless, now let us go back to our problem. Now you can see that the set under consideration is collection of all x such that some h of x equal to 0, where h is measurable. And hence that set is measurable. Are you with me? Is it okay?
Yes, sir.
Yes, sir.
So this is now if you want to complete, note that lim sup inf, lim sup fn and lim inf fn are measurable. And hence collection of all x in E such that lim sup fn minus lim inf fn is equal to 0, equal to some number, some real number is measurable. Okay. Now, what is the issue if it is extended real valued? I have put the question as extended real value, but I have to think. Suppose it is extended real valued function, then the lim sup fn minus lim inf fn. Possibly it may be
Infinity minus infinity case.
possibly it may be infinity minus infinity, and in that case I cannot consider this set. That's for sure. Okay. So collection of all x such that lim sup fn minus lim inf fn, that approach I can't do. But still, whether the same question can be tackled if it is extended real valued. Okay. So let us think over it. I don't know. I have to think whether it is a mistake. I just put extended or extended can be included. Okay. So we have solved the problem partially without considering the extended real valued. So all of us can think. Maybe tomorrow you can come with some input. Question is, what if f is extended real value? Whether still it will be okay, the result is okay. Of course, this approach will not work. That is okay because of this issue, lim inf minus lim sup. And remember, even if lim sup and limit is infinity, in the extended real valued, what we call is convergent. So convergent doesn't mean that limit cannot be infinity in the case of extended real valued. Okay. So from convergence, we cannot say lim sup and lim inf will be finite. That we cannot say. What if f is extended real value? I don't have an answer right now. Maybe I can think. Okay. Are you with me? Are you people there?
Yes, sir.
Yeah. So for extended real value, you can also think over it and let me know. I will also. I am not sure whether it is a mistake I put or extended can be included. Still the result is true or not. The issue is when you talk about extended real value, even if the limit is infinity or minus infinity, the sequence is convergent, not divergent. So it may be possible that both lim sup and lim inf is infinity, and it may be possible that both lim sup and lim inf is minus infinity. Maybe you can consider those two cases separately and see. You consider the case when lim sup equal to lim inf equal to infinity. That is, limit is infinity. And also you consider the case when limit is minus infinity. Okay. But anyway, I don't want to include the discussion right now. Next question is monotone functions are measurable. I think I have mentioned it in the lecture yesterday. And the simplest argument will be like this. Once the function is monotone, it is continuous almost everywhere. Okay. Monotone functions are continuous almost everywhere. And you know that if a function is continuous almost everywhere, then it is measurable. Okay, that's how we argued in one of the theorem yesterday I proved. But in fact, you can do it directly without using continuity, etc. Okay. Can you have a try? You have a function f from R to, we don't know, maybe R star, but let us consider R to R or E subset of R to R, and f is monotone. This is given. You are asked to prove that f is measurable. For that, you have to prove that the inverse image of an interval is measurable. That is one way. Or you can prove that set of all x such that f of x greater than alpha or f of x less than alpha, these are all measurable. Okay. So what do I do? Let us consider this, for instance. Collection of all x such that f of x greater than alpha. Alpha is a real number. Look at this. If you can prove that this set is measurable, we are done. Okay. Set of all x such that f of x is greater than alpha. Suppose you have a particular x for which f of x is greater than alpha, and suppose y is greater than or equal to x, then f of y also will be greater than alpha. Isn't it? I repeat, suppose you have an x naught, fixed x naught, for which f of x naught is greater than alpha. You know that f at x naught is greater than alpha. Then you take any y greater than x, f of y also should be greater than alpha. Yes or no?
Yes, sir.
So from this, do you see that this set should be an interval?
Yes, sir.
I am just claiming it. You should convince yourself. It's an interval. Look at this. I claim that this set is an interval. Whether intervals are measurable?
Yes, sir.
And
Yes.
hence measurable. And hence measurable.
We don't know if E is an interval.
E is not an interval. I don't know. Okay. That's why I'm saying whether I can prove collection of all x in E for which f of x greater than alpha is an interval or not. If E is an interval, it is clear. But suppose E is not an interval, but just a set. First of all, can you talk about monotone? Yes, you can talk about monotonicity because I have to just consider x comma y is in E, x less than y. This should imply f of x less than or equal to f of y for monotone increasing. So it is not necessary that to define a monotone function, the domain should be an interval. Only thing that what we need is whenever x and y are in E, x is less than y, then I should be able to say f of x less than or equal to f of y. So monotone functions can be defined on a set which is not an interval as well. But question is, can we see collection of all x for which f of x greater than alpha is an interval, even if E is not an interval? Can I see it? I'm not claiming I can. Okay. Is it true or not? What do you
No.
think? Do you have an example?
So we can take identity function from rationals to R. It will be increasing.
How do you say it is increasing?
I'm taking identity function from rationals.
Identity function on Q. Okay. And you define your monotonicity like this. Whenever x and y are in the set and x less than y, you should have, right, fx less than fy. So you are right. In that case, your domain is Q.
But sir, this set will be intersection of two measurable sets, an interval and E.
If you are, so first of all, I should, but I am not given with E is measurable. So I think this question needs some clarification, because see, suppose I take f is a function from E subset of R to R and monotone. To define monotone, you don't need E to be measurable. Yes or no?
Yes, sir.
To define a monotone function, it is not necessary that the domain is measurable. Whereas to define measurability of a function, the blanket assumption we make is that the domain is measurable. And therefore, I think the question is incomplete. I should mention monotone functions on which set. Okay. So I think I will correct the question. Either I will take f from R to R, or I will take f from E subset of R where E is interval. Okay. Now when E is measurable, we will see whether it will be still hold. So let me correct the question like this. Let f is a function from E subset of R to R and E is an interval. Then it is clear. And suppose f is monotone. Okay. Then because E is an interval, this part is clear. Okay. If not interval, at least measurability I need. Otherwise, I cannot talk about the measurable function. Do you agree with it? I'm asking you, do you agree with it? Question is this. At least measurability of E is needed, the domain. Otherwise, you cannot talk about measurable functions, right? Yes or no?
Yes, sir.
Yes, sir.
So implicitly, it is at least assumed that the domain of the monotonic function that you are taking is measurable. Okay. Now question is this. Suppose f from E subset of R to R and E is measurable, but I don't know whether it is interval or not. E is measurable and f is monotone. Whether still the result holds or not. This is what we want to see. F is monotone. Okay. In this case, what will be the collection of all x such that f of x greater than alpha? This x should be in E. We are in E. Okay. So can I say that this will be E intersection and interval? That's what one of your, I don't know the name. That's what one of your friends was suggesting. Can I say that this is E intersection and interval? I'm not sure. I have to E intersection and interval. Is it right? If yes, again we are done. Interval is measurable, E is measurable, therefore this is measurable. Can I see that? Using the fact that whenever x is in E, first of all, what is the definition of interval? Okay. What is the interval definition? You might have seen a connected set in R is an interval. So how do you define interval in R?
2 points A, B in interval, then T of TA plus 1 minus TB is also in R.
That is convex, right? Is it not a definition of convex? So anyway, you have to recall the definition of interval and you have to see whether this set collection of all x in E such that f of x greater than alpha is somehow you can write as E intersection interval. I feel it should be true, but I don't have a rigorous argument. I have to think over it. Okay. But anyway, the question has to be polished. I cannot just like that say any monotone functions are measurable. What is the domain of that function? And whether that domain is a measurable set, that's a question. Otherwise, you cannot talk about measurability. So definitely that question has to be polished. Now, how to polish? Of course, the simple case would be take f is a function from E subset of R where E is an interval. Then it is very clear. But if E is not an interval and E is measurable, can I have the same result? I don't have an answer, to be honest. Okay. Maybe I will postpone this again. Again, the second question is also only partially solved in case E is an interval. Okay. You think over, come with some input. I will also think. In case your E is an subset of R, measurable, that is for sure is needed. Otherwise, you cannot talk about measurable function, but not an interval. Then can I somehow prove that monotone functions are measurable? Okay. So I should accept that the question is vague in the sense it is silent about what is the domain. That's not correct. I should specify what is the
If we take fx is greater than equal to alpha and we take the point where alpha is attained, then the interval will be where the point is attained to infinity.
See, greater than alpha or greater than alpha equal to alpha doesn't matter. Okay, so now I am including greater than equal to alpha. What's your point?
And we take a point where alpha is attained.
That we don't know, right? Whether it will be attained or not, because this should be true for any alpha, not a specific alpha. So what is the condition of measurability? Collection of all x such that f of x greater than alpha should be measurable for any real number alpha.
If
So
alpha
attaining point we cannot always guarantee.
it is not attained, the set will be empty.
For a particular alpha, suppose f of x, what are you saying? For a particular alpha, if there is no x such that f of x is greater than alpha, okay.
The set will be empty and E intersection empty is empty.
Hmm.
And if
Okay.
it is attained, then the set will be an interval.
Why it should be an interval in that case?
So if alpha is attained at
So
some
1 minute. Let me write 1 minute. 1 minute. Please hold on. Suppose there exists an x naught such that f of x naught is equal to alpha. This is what you are saying?
Also, so we can assume
Starting.
for in increasing function, then we can prove it for in decreasing function too.
That's okay. That's okay. Monotone increasing we can do. That's okay. And suppose f is monotone increasing. I'm just trying to write the solution from what you are saying. Okay, since we are in online mode, it is difficult to understand what you are saying. Suppose f is monotone increasing. Okay.
For any y naught greater than x naught.
That's okay. For every y greater than or equal to x naught in E, x naught and y in E, that's where I don't know whether this y will be in E or not. Okay. Then f of y will be greater than or equal to f of x naught because of monotonicity, and this will be greater than alpha. Okay, and that will imply that y is also in that set, right? If you call this set as A. This is what you are saying, right?
Yes, sir.
But again, the issue is this. You are taking a y greater than or equal to x naught and y in E. Then only I can talk about f of y.
We are picking a y from an interval which is in E. So E intersection the interval.
I don't understand. Sorry. How you are picking a y in an interval? I am talking about this set. I am not in interval now. I am just looking at A. I am just looking at A. Okay. Maybe your argument is right. You may have to write it properly and send it to me. Then I can have a look. Anyway, so instead of spending too much time on it, now what I will do is the following. The question is clear that it is incomplete. I have to mention the domain of f. So now the issue is whether the domain can be only interval or it can be non-interval as well. That we have to answer. If it is an interval, we can prove that result without any issue. If it is a measurable set, but not an interval, whether the result is true, if yes, how to prove it? If not, can we get a counterexample? That last part is missing. Okay, so that we will do. We will think over it. Okay. The purpose is not just to supply the solution. Through discussion, several other questions can come, and that's how we should learn. So that's okay. So again, let me repeat, since we had certain confusion, let me repeat the points. No doubt that the question has to be polished. I have to say what is the domain of the monotone function. No doubt that the domain should be assumed to be measurable. If not whole R, if it's only subset of R, I should assume that it is measurable. Okay. Now the question is, in case it is measurable but not interval, whether the result is true. We could not prove it. Okay. There are chances that the result is still true. We have to get a proof for it. But I cannot use the fact that collection of all x in E such that f of x greater than alpha will be an interval. I cannot use that fact. But using some other fact, can I still prove this set is measurable or not? I don't have an answer. So those who have given an inputs, please sit down and write your argument and see. Okay. Anyway, I will try once again. So having said that, again, first question also has some loose end. Can we have only real value or can we also have extended real value? So there is a loose end for first question. There is a loose end for second question. Anyway, so please think over it and let us discuss in the next lecture or through email. Now coming to the third question, f is from R to R continuous function and g from R to R a measurable function. Show that the composite function is measurable. At least there it is clear, everything is given explicitly, the domain and codomain. Okay, like that I could have mentioned the first two questions. Anyway, so before solving this, I should give you a connected question, namely, please try to prove that composition of two measurable function need not be measurable. Okay, try to get a counterexample. For the fact that f comma g from R to R measurable, does not imply f composite g or g composite f composite g is measurable. Okay, so you can try that. I would give you a hint. You can seek help from Cantor-Lebesgue function, which I introduced in the last lecture. As I told you, that function is going to be counterexample for many facts in measure theory. Cantor-Lebesgue function. Okay, so now let us prove the question in demand. F is a continuous function, G is measurable, the composite is measurable. Now, let f from R to R continuous G from R to R measurable. Somehow I have to prove that F composite G is measurable. One of the set we have to consider to prove something is measurable. So let us consider X in R such that F composite G of X greater than alpha or greater than or equal to alpha. I should prove that this is measurable for each alpha in R. Let alpha in R and look at this. Can I somehow say that this set is measurable? Okay. Let me try. Set of all X in R. F composite G of X. By definition, this is F of G of X. F of G of X is greater than alpha. Okay. Can I rewrite this as collection of all X in R such that, how did I write? G of X. If F of G of X should be greater than alpha, then G of X should be in F inverse of alpha infinity. Think over a while and tell me whether you agree with this. F of G of X greater than alpha. That is same as saying G of X is in F inverse of alpha infinity. Do you agree?
Yes.
Yes, sir.
Inclusions you can try, set inclusion. Okay. Suppose F of G of X is greater than alpha, then whether you will get G of X this, and conversely, suppose G of X is in this set, okay, then can you get F of G of X is greater than alpha? Okay. Now, what is given to you is F is continuous. Remember, alpha infinity is an interval. And F is continuous. Since F is continuous, inverse image of an open set is open. So in particular, inverse image of an interval, open interval is open. Okay. Therefore, F inverse of alpha infinity is an open set in the domain. But domain is R. And open sets in R are union of disjoint open intervals. Okay. Therefore, F inverse of alpha infinity, I can write as, let us say, union Jn. Yeah. Jn's disjoint open interval. Agree? Do you agree? What is the fact that I have used is the only that inverse image of an open set is open because F is continuous, and an open set in R is a countable disjoint union of open intervals. That's it. Okay. Now let us go back to the set under consideration. Therefore, collection of all X in R for which G of X lies in F inverse of alpha infinity, okay, is same as collection of all X in R such that G of X is in F inverse of alpha infinity is union N Jn. Okay. And I claim that this set is collection of all X in R such that X is in union N G inverse of Jn. Again, I will leave it to you to verify this. Okay. Collection of all X in R such that X is in union J inverse Jn. But this union J inverse Jn is anyway in R. So in fact, I can say that this is exactly equal to. So this will be equal to union, union N G inverse of Jn. This is my claim. Convince yourself with this claim. If I am wrong, you can get back to me. So, but now G is measurable. Jn's are intervals. Since G is measurable and Jn's are interval, G inverse of Jn's would be measurable. Okay, using the fact that once G is measurable, G of x greater than or equal to alpha, G of x greater than alpha, less than alpha, less than or equal to alpha, all are measurable. Using this, you should be able to see that G inverse of an interval is measurable whenever G is measurable. Okay, this is measurable. And countable union of measurable set is measurable, and hence this is measurable. Okay, so this place you should convince. So this is the hint for third question and fourth. That's a nice question. F from R to R be a measurable set and B be a Borel set. Show that F inverse B is a measurable set. F is a function from R to R. B subset of R. B is Borel. Keep the definition of Borel in mind. You have a sigma algebra and you have a topology on R. You consider the smallest sigma algebra containing all open sets in R. Okay. That sigma algebra is called Borel sigma algebra, and the elements in the Borel sigma algebra are called Borel sets. Okay. This is true in general. Given any topological space, you can think of a smallest sigma algebra containing the topology, and that is called a Borel sigma algebra. And the elements are called Borel sets, or sometimes also called Borel field. Okay, so that is just to recall the definition. Now, what you have to prove? F inverse B is measurable. Claim F inverse B measurable. Okay, I think I have approached in this following way. Let us consider the collection of all E subset of R for which F inverse of E is measurable. F is not given to be F is given to be measurable. F is given to be measurable. Now I am considering the collection of all E subset of R such that F inverse E is measurable. I claim that this collection of subsets of R forms a sigma algebra. Claim A is a sigma algebra. For that, I have to see whether it is closed under union, countable union, closed under complementation, etc., etc. Okay, and null set is in A is clear. F inverse of null set will be null set, and it is measurable. Therefore, null set is in A. Now let us see if ENs are in A. N belong to N. That implies F inverse of ENs is measurable. My aim is to see that union En is in A. But fortunately, F inverse respects union and intersection. F will not respect union and intersection, but F inverse will. Okay. F inverse of union En not implies. This is a fact from set theory. Is equal to union N F inverse of En. Okay. Therefore, each F inverse En measurable, we have this. So that implies F inverse of union En is measurable. And that will also imply that union En is an entity in A. Okay. So whenever Ens are in A, union En is in A is closed under countable union. Now for complementation. Note that F inverse of A complement, or let us say E complement, is equal to F inverse of E complement. In general, F inverse respects all these set operation, union, intersection, complement, and complementation, etc. But F will not. In general, F will not respect. Okay. So now use this fact. Therefore, if E is in A, that implies F inverse E is measurable. And that will imply F inverse E, the whole complement, is measurable. And that will imply, using the previous identity, E complement is in A. So A is closed under complement and so on. And thus A is a sigma algebra. Now I claim that A contains all intervals. A contains intervals. More precise, A contains all open intervals. That is easy. If you write AB, I will just show for this finite case AB, and then other things you can similarly see. AB you can write as, let us say, I want to write it as intersection. Minus infinity B intersection A infinity. Okay. And once F is measurable, collection of all x such that F of x greater than A is measurable, F of x less than B is measurable. So AB will, this intersection will be measurable. So A contains all intervals. So I am not writing the details. This is my claim. And towards that claim, this is the hint. You develop with this. Okay. So the basic facts that we need is the following. A is sigma algebra, which already we fully proved. And A contains interval that I have claimed with the hint. Now use these two facts. So A is a sigma algebra containing all intervals. Okay. Once a sigma algebra contains interval, it contains all Borel sets. Do you agree?
Yes, sir.
Why is it so?
Every open set is collection of.
Or you can easily say that Borel sigma algebra is the smallest sigma algebra containing all intervals. And this is an sigma algebra containing all intervals. Okay. So with these two facts, again, I am not writing the details. Hence, A contains all Borel sets. Club these two facts. A is a sigma algebra, A contains all interval, and try to convince yourself that A contains all Borel sets. And we are done. Once A contains all Borel set, what does it mean? It contains, suppose I take B in B, that implies whenever B is a Borel set, that B will be in A. And B will be in A means F inverse B is measurable. F inverse B is measurable. The gap is here. Why do I claim that A contains all intervals? Fill that gap. The next question is, yeah, this I promised in the class, but I could not get time to do that. So that's why I have included here. If you remember the Lebesgue measure on R, in that point, we have introduced three collection of subsets of R. One is obviously the power set of R, 2 power R, which is evidently a sigma algebra. Then we introduce the collection of all measurable sets, Lebesgue measurable set, which is proved to be a sigma algebra in our lecture. And then we introduce collection B, which is the smallest sigma algebra containing all open sets, which is same as saying smallest sigma algebra containing all open intervals. Okay. This is power set. This is sigma algebra of all Lebesgue measurable set. And this is Borel sigma algebra, meaning smallest sigma algebra containing all open sets in a topology. Here, smallest sigma algebra containing all open intervals. And therefore, by the very definition, B is contained in M. And you have seen that there are examples of sets which are non-measurable. Okay, so M is contained in 2 power R and M is not equal to 2 power R. So this part we have done. The question is whether B will fill entire M. Okay, whether every measurable set will be a Borel measurable set. Okay, that part we have not done. Okay, so that and the purpose of this question is to include that part. Now we claim that B cannot exhaust entire M. B is strictly contained in M. So you have to find a measurable set which is not Borel measurable. Okay. Again, as I told you in this measure theory, especially with measurable functions, integration, etc., Cantor function will give you many counter examples and it will help you in many cases. So again, here also I am going to make use of Cantor set. Okay, we shall make use of Cantor-Lebesgue set. There are several ways to Cantor-Lebesgue function. Several ways to approach Cantor function. One way I have introduced yesterday using construction, like Cantor set, phi 1, phi 2, etc., and then take the limit that will give you the Cantor-Lebesgue function. Okay, there are several other ways, and I have given you some references to explore. Okay, so let us assume that we all know what is Cantor function and some properties of Cantor function. One is that Cantor function is measurable. Note that I am assuming this result. Cantor function f from 0, 1 to R. In fact, it will not be into R. It's a subset of R. I will tell you what is that subset. Is measurable. If you want, I can introduce Cantor function once again, reintroduce in the following manner. Okay. There is another way to look at Cantor function, how to define it using expansion, ternary expansion and binary expansion. Before that, do you know how to write an n-ary expansion of a? What do you mean by decimal expansion, binary expansion, ternary expansion, etc. of, say, let us fix an x in 0, 1. I have an element x in 0, 1. For instance, let us take x is equal to 1 by 4. Okay. You all know what is it, decimal expansion is 0.25. But do you know how to construct a decimal expansion? How do you define a decimal expansion for a number in 0, 1? The approach is this. I don't know whether I have introduced this while I introduce Cantor set to you, but let me redo it. Okay. To get a n-ary expansion of a number, I am just following the Simmons approach and I found it very interesting and without any ambiguity. What you do is you divide, if you want a ternary decimal expansion, you divide this 0, 1 into 10 subintervals of the form 0, 1 by 10, 1 by 10, 2 by 10, and so on, 9 by 10, 1. Oh, sorry. left close, right open. I'm not considering 1. And you assign these intervals the number 0, 1, etc. up to 9 in the ascending order. So the interval 0, 1 by 9 is labeled with 0, 1 by 10, 2 by 10 is labeled with 1, and so on. Now you look at 1 by 4, and what you are searching for is decimal expansion. Okay, we know it is 0.25. How to get it is the question. Okay, so look at 1 by 4 and determine in which subinterval this lies. 1 by 4 lies. Okay. Can you tell me? In which subinterval 1 by 4 lies? Assume you don't know 0.25. Okay, you know 1 by 4, and from 1 by 4 you determine which interval it lies. Yes. Is it that difficult? Do you see that it will be in 2 by 10, 3 by 10?
Yes, sir.
So here it lies. Okay. And what is the label corresponding to that interval? What is the label corresponding to that interval?
1.
No. 2
2.
by 10, 3
2.
by 2. Okay. That will be the first digit after the decimal point in the decimal expansion. Okay. So that's how you got this 2. Okay, so you already determined where that 1 by 4 lies. It is in 2 by 10, 3 by 10. Now you again divide 2 by 10, 3 by 10 into 10 equal intervals, half open, and then label it with 0 to 9. So 2 by 10 is actually 20 by 100. So next one will be 21 by 100. Then 21 by 100, 22 by 100. And so on. Last one will be 29 by 100, and this will be 30 by 100. Okay, and label that it with 0. Give me 1 minute. 0, 1, 2, 3, etc. up to 9. Okay. Now you look at 1 by 4 and see in which subinterval of 2 by 10, 3 by 10 it lies. Okay. 1 by 4.
26 by 100.
Pardon? Are you here or you are talking something else? 1 by 4 is 25 by 100. Okay. And therefore it is here 24 by 100, 25 by 100. No, that is open. The next one. Okay. The next one 25 by 100, 26 by 100. And what is the label corresponding to it? Do you see that it is 5?
Yes, sir.
And that is how you got 0.25. Okay. Now you can continue this. So again, you determined already that it is in 25 by 100, 26 by 100, I hope. Okay, 1 by 4. Now you divide this into 10 subintervals. Okay. And next point, if you want, you look at which subinterval it is. It is again here. You will get 0.25000 and so on. Okay, so that's how you got 1 by 4 decimal expansion. Now, why decimal? This can be done for ternary expansion or binary expansion or anything. Suppose I want binary expansion for 1 by 4. Binary expansion. Can you quickly tell what I have to do? I have 0, 1. Okay. Divide into 2, not 10. Divide into 2. 1 by 2. Okay. And label it with 0 and 1. Look at 1 by 4, where it lies. It is in 0, 1 by 2. Okay. So the first digit after the decimal point in the binary expansion will be 0. So 1 by 4 will be 0.0. Now next. So you have determined that it is in 0 half. Okay. Now divide into 2. It will be 0, 1 by 4 and 1 by 4 half. Okay. This contains the label 0 and this contains label 1. And 1 by 4 is here. So next digit will be 1. So 0.01, I don't have to write the 0 in front. 0.01 is the binary expansion for 1 by 4. Okay. Similarly, you can go for ternary expansion. Let me close with this following observation. Now you look at Cantor set. Okay. You know how to construct Cantor set by removal of middle third interval. I claim that Cantor set consists of precisely those points whose ternary expansion does not contain the digits. Which digit will not be there? Cantor set contains precisely, I will stop with this, those points in 0, 1. Let us take Cantor set in open 0, 1. Whose ternary expansion does not contain the digits. Can you guess?
1.
Why is it so? In the ternary expansion, what you do is 0, 1 you will divide into 3. 0, 1 by 3, 1 by 3, 2 by 3, and 2 by 3, 1. Okay. And the label for this is 0, label for this is 1, and label for this is 2. And what you're removing is 1 by 3, 2 by 3. So the first decimal point does not contain 1. Okay. Now to get second decimal point, what you do is take 0, 1 by 3 and divide into 3. Or 2 by 3, 1 and divide into 3. Again, the middle third you are removing, and the middle third carries the label 1. Okay. So no decimal no digit in the not decimal expansion, ternary expansion will contain the digit 1. Okay, so this will give you an idea of what are all the points contained in the Cantor set. Okay, and this is useful description. With this, you can prove that Cantor set is uncountable and many things. Okay, now with this in mind, I can also define Cantor function. Since we don't have time, I will stop here. And using Cantor function, I will prove this, that there are measurable set which are not Borel sets. I will seek help of Cantor function. Okay, so let me stop here. We will meet tomorrow again.